Okay, let me say a few words in Russian. Ну, я хотел представить нашего гостя. Он, как вы видите, он из Texas, но его интересы в области оптимизации и во многом применительно к энергетике, и сегодня это будет как раз доклад посвящен. Бисмарк сотрудничает со Сколковым, как раз с энергетическим центром Сколково, с которым и мы несколько связаны. Так что тут есть общие точки интереса. Ну вот, но, собственно, все остальное. И you're welcome,
Thank you. So my name is Bismarck Singh. I'm a PhD candidate at University of Texas at Austin. I work in applications of optimization to energy, renewable energy, and also to healthcare and public health. This talk is only about renewable energy. So there are two topics inside it. Both of them are completely separate and very little overlap in the two. So if you do not like one, maybe you will like the other. We will start with the first topic, which is on a wind farm system. So the situation is that you have a wind farm. You want to make money from producing electricity. You will promise that tomorrow at 9 a.m. I will supply you maybe 10 megawatts of energy, but you are making a promise for tomorrow. So you do not know how much wind will be out there tomorrow. So you will meet this energy from a backup diesel generator. So when wind will be very little, you want to run the generator, and when the wind will be very high, you can maybe switch off the generator. The issue is that you must meet your promise. So if you promised 10 megawatts, then the operator of the system does not care whether you meet it from the wind or from the diesel, but there is a very high penalty, so you must meet the promise. So here we make an assumption. In reality, what happens is that if you promise very high and you give too much, so that surplus energy can be used for another system generator who is supplying you less, but we do not do any balancing here. So we say that you have promised some 10 megawatts and you definitely want to achieve. So how should you schedule your generator so that when should you run generator and when should you get the energy from the wind? The issue is that wind is very stochastic. It is difficult to forecast. So you do not know, because you do not know the output of the wind very certainly, so you do not know how much generator to run as well. So here is an example, something I picked from Google. So some plant in Germany, the forecast of the wind varies a lot. So in the summer there is little wind, and in the winter months there is much more wind. But the scale of this graph is not good because it is by month. If you make it by minute, it is better. Then you can see that even on a scale of minutes, maybe there will be storm coming outside, and then the next hour there is no wind. So it is difficult to forecast. Okay, so my interest is in optimization models. So we build some model to solve this. So we have some set of time periods, maybe 24 hours for one day. We have some scenarios of the wind. Scenario of the wind means that one scenario is, for example, that at 9 a.m. there is 3 megawatts of wind. At 10 a.m. there is so much wind. At 11 a.m. there is so much wind for the full day. Then the second scenario is that at 9 a.m. so much wind. At 10 a.m. so much wind. So we build many forecast scenarios for the different outputs of the wind in the day. But they are finite, and this n could be something very large. But the important thing is that this is all data. So this is done before any optimization. There is some cost of generating electricity. There is some price with which you will supply energy. This is your profit. You know how much wind will be produced in what scenario. So that means that in, for example, at scenario 1, Wt of omega, so omega equals 1, at T equals 9. So at 9 a.m. under scenario 1, maybe you have 3 megawatts of wind. For each of these scenarios, there is some probability, and there is some maximum capacity of the generator. So this epsilon here is, so you definitely want to promise to the system operator that for sure I will give you 10 megawatts tomorrow. There is some leverage which is allowed, so maybe 95% of the cases you will surely be honest and promise him whatever you will actually deliver. But there is some 5% chance that there was just no wind and you cannot supply energy. So we assume that there is some contract which is signed between you and the system operator, which allows you that there is some small percentage, 2, 3, 5%, that you can fail the promise. For other small values of epsilon, you must meet the promise. So this is a very central assumption to our work. I will explain more of it later. There is some energy which is used from the generator. There is some energy which you promise that you will deliver. And then there are some other variables. We don't need to look too much into this yet. One thing important is that the decision variables are deterministic. So there is no omega on this. So this means that you have promised that tomorrow at 9 a.m. I will supply you this much energy, irrespective of how much wind there will be. You have also promised that how much energy will you use from the generator tomorrow. So you have said, for example, that at 10 a.m. at 9 a.m. I will give you 10 megawatts of energy, and I will use 8 from my diesel generator. So you have made deterministic promises for both of these decisions.
Sorry, but why cannot you decide online how to use a generator?
Because
your own decision, your internal decision, nobody sees.
That is a good question. There are two answers to this. One is the physical answer, and the other is the mathematical answer. So the physical answer is that sometimes, so this came from our discussion with some power system operators, that they want to build a plan before so that they can come up with a schedule in which they don't have to dynamically run the generator. It is less profitable, it will cost them more money, but they do not have to do more planning in real time then. They want to make a schedule that this is what we will do tomorrow. So it will be a deterministic set.
So it's not your generator?
It is your generator.
It's your generator?
Yes.
But power company, how, it's your business how to use your generator?
There are also...
Turn it on or off?
Yes, but...
Why should you have a plan for this? You are the only user of this plan.
Yes.
What power company? Why do you supply them with your plan of use your generator?
It is for logistics that if you have the generator running for few time periods, then you cannot switch it off immediately. And you want to have a schedule so that everything else in the plant is known in advance. So this assumption we will relax later in the model. So later on this decision variable will be stochastic. The second answer I will tell you in a minute, but it is because the problem becomes more hard if you do it.
Okay, so can I ask a question in connection with that? Because the energy production is not stable, it's stochastic, you say. Do you have these wind power station accumulator to accumulate energy and to put to the, to somewhere?
So no, so we have only one wind farm. no accumulation from other wind farms, just one farm.
So no accumulated?
No. No balancing, no accumulation, just one wind farm, one generator of some capacity.
So no ways to storage.
No, no storage also.
And what is worth in that kind of energy, because it's not stable? For what purpose can you use it?
So the forecast is fixed. So you want to give a firm fixed output, stable output. The sum of the generator plus wind is fixed. Wind is not stable.
But power is stable.
The output is stable, yes.
Output what?
The total energy which you supply, it is stable.
Should be stable.
Mm-hmm.
Unless you want to meet penalties.
Yeah, so you cannot say that, oh, there was no wind, sorry, I cannot give you energy now. Or, oh, there is more wind, I will give you more energy now. So this is an assumption. In reality, if there is more wind, you can give more energy, but you have to pay some penalty.
But it's not clear how to do that, because the wind is not stable.
Oh, so
To stabilize the output.
it is, yeah, I will tell you how we stabilize the output.
Could you please go one slide before? The variable R and V, it looks like describe the same thing because.
Okay, so there is some physics of the diesel generator which says that if you switch on the generator, then it must remain on for some time. So, similarly, if you switch off the generator, R tells you that is your generator on or no. U tells you that did you just switch it on or no.
R and V.
Yes, so R is on.
It means that it seems that if R is 1, then V is 0, and vice versa. Is it true?
Maybe you meant that V is 1 if generator is switched off
No.
at time 10.
Mm.
That would make sense.
Oh, yeah, I see. Yeah, sorry, it's a typo. Yeah, it should be switched off. Yes, sorry.
My question is that epsilon, the contract is when you produce something less than epsilon, you are not fined. So the system operator allows you to fail your promise for epsilon for free, or you are penalized.
He allows you to fail it for free.
Okay.
But epsilon is very small, so maybe like 2%. So our reasoning for this is that if you will fail for maybe 10%, then he will say, I don't need you. I can get energy from another farm.
From 2% to 10%, you
10%.
are penalized
With the same penalty. So we will make it not even 10%, like 5% or something. But the idea is that there is no penalty beyond it. Okay, so this is our optimization model. We want to maximize profit. Profit is revenue from generating electricity. This is what the system operator pays you. Y is what you promised. This is the cost from the diesel generator. So you have to pay some money to run the generator. So the difference gives you the total profit. Let us wait for this constraint and let's look at this first. So these are constraints which govern the physics of the generator. It is a lot of math, but what it means is that there is some ramping of the generator. For example, if you're running the generator at 10 megawatts now, in 5 minutes you cannot run it at 100 megawatts. It has to go through some gradual change. So maybe from 10 you can only make it 12 in the next time period. And similarly if you are decreasing. Then these constraints also say that if you switch on the generator now, then it must remain on for maybe 2 time periods or 3 time periods, and if you switch it off, then it should also remain like this. Then there is some maximum capacity of the generator. In reality, there are more constraints which govern, you can add many more constraints to make the generator feasible region different. For example, you can add a fixed cost, or you can add some head, which is that the power output depends on the load of the generator, but we do not do this. So this set small x in capital X, it denotes the feasible region of the generator. This set is very well studied in literature, and actually these constraints without the ramping, they form the convex hull of this, so it is the best you can do. People have done a lot of work on this, and our aim is not so much in this region, but in this constraint. So this constraint, let us try to understand it. Let's look at the term inside the brackets, inside the parenthesis. The left hand side tells you generator plus wind.
So just one question, please. And the costs are linear in
Yes.
generators?
Yes, it is also an assumption. So you can,
C sub t is a constant
yeah,
for each t, but it can change in time.
yeah. Yeah,
Depends on time. So
yeah,
night use of the generator is more expensive than a day use of the generator.
yes,
That's possible.
yeah. When we do our numerical analysis, we take C of t to be the same for each time period, but we just write it to make it more general.
But it should be linear.
Yeah, so people study C of t as a function of x of t. So there is some fixed cost and some operating cost, and the operating cost is non-linear, but we do not go into that territory. So our whole aim for this project is how do we formulate this constraint, which I will tell you. The other things, like you can make it more complicated, but we are not so interested in those things. So let us look at this constraint now. The term.
You said that epsilon is not a probability, but a threshold which you can diminish your supply without any penalty. So 2% is the amount of supply you can fail to, the amount of your heat you can fail to supply.
Mm-hmm.
It's not a probability. Why should you
No, wait.
formulate it this way?
I will explain it. So the term inside the round parenthesis, the left hand side tells you generator plus wind, so this is the total which you are producing. That must be at least your promise. So, and this should be for all time periods in the day. So this is stochastic, so the probability is taken with respect to this, and the joint probability for all time periods, it must be some threshold. Epsilon is small, so this side is like maybe 95 or 99%. So the joint probability that you meet your promise is very high. Now to understand this, and this is important, let us imagine that t is 1. So you can write this constraint by taking the inverse, because this is just the cumulative distribution of the following decision variable, and you can write this thing analytically, then you can solve this program. If t is 2, you will have to take a double integral, because the probabilities will be correlated, and maybe you can solve it. For t equals 3, a triple integral, you will have to use some numerical integration, or maybe Monte Carlo, and so on. But you know that when the dimensionality of t increases, the errors in numerical integration will blow up, so you don't want to do this. So our aim is that we want to represent this constraint exactly without an approximation. And how can you do this in an optimization method? Yeah, so we will look at this constraint in more detail. So constraints such as this are known as joint chance constraints. They occur a lot of times in literature. Whenever you are modeling any risk scenario in some decisions. So there is some risk, some uncertainty, and you have some decision variable y, and you have some constraint like this, then these constraints occur. So they are difficult to solve for two reasons. One, that if I give you a y, it is difficult even to check is this constraint y feasible or not because of the dimensionality of t. Second, that this constraint in general is not convex. So if the distribution is normal, you can do something and maybe write down an expression, but for a general distribution, it is not easy to write down an expression. Further, in this problem, if you have nothing in this region, so if this is empty, still this problem is NP hard. So this makes it challenging to solve it. Okay, so to do this exercise, you need some samples of the wind. So we can generate the samples of the wind using historic data, or you can build some sort of a forecast for the wind. So we build a simple forecast model to predict wind output. So people spend a lot of time in forecasting wind accurately. We just use one model, which is reasonably reliable, but not the best in literature. So this is our forecast, but we will generate some samples around this forecast. So this gives you the mean of the forecast, but you will have maybe 1,000 samples up and down of this, or something more. So our aim is that you want to have a lot of scenarios of the wind, so that you can use it in your chance constraint. Okay, so now we will go back to this constraint and see how you can solve this. So here is one method. You can define a decision variable z, which is 1 if you satisfy the promise. So the constraints can be represented as follows. So imagine that z equals 1, then the right hand side is 0. Then this constraint means y is less than x plus wt of omega. So that means that your promise is satisfied. So z equals 1 means that you satisfy the promise. Z equals 0. So then this term finishes, and the right hand side is m. M is something very large. So this constraint means nothing. So you want z to be 1 for many times. How many times? This constraint tells you that at least some 1 minus epsilon times this should be satisfied. So these two constraints represent the joint chance constraint exactly, meaning that if you solve this, you get an exact solution to the joint chance constraint.
And what is P omega?
P of omega is the scenario, is the probability of scenario omega. So it is simplest to think of P of omega as 1 divided by n. So this will give you some number of z's which must be 1.
So you are penalized even if you fail to supply equivalent quantity of electricity. Even for
Sorry,
1
sorry,
hour.
sorry,
You are
say.
penalized if you do not meet your promise even 1
Yes.
period a day.
Yes.
And it doesn't matter, 1 or 2 periods, the penalty will be the same.
So it will be, he will say that if you do not supply in 1, I do not want energy for you for the whole day. So this is like a knapsack constraint, and so these two constraints will give you the formulation exactly. But you do not want to use this in your optimization, because the relaxation of this is not good, and if you will solve this, it will take a lot of time to complete, because there are decision variables which are binary, and the linear programming relaxation is not good for such models. So this is another method to do this, which is much improved from the previous method. So take the scenarios of the wind and you will sort them in ascending order. So for 9 AM, for each time period, you will take the smallest wind scenario, then the second smallest, and then the third smallest, and arrange them in order. You do this for every time period. So now the scenarios are jumbled. So it could be that the smallest scenario at 9 a.m. is maybe 53rd, and the smallest scenario at 10 a.m. is maybe 32. So you have to keep track of the ordering here. But this will give you some better results. And you can take the difference of the two consecutive scenarios of the wind, and that will always be non-positive by this construction. So you have some variable delta. So why are we doing this? Our idea is that if you know that you will satisfy your promise when wind is maybe 10 megawatts, then you know that you will also satisfy it at 11 megawatts. So you don't need to worry about scenarios of the wind in which wind is producing more than some amount. So if you can find out what is this minimum amount, then everything above it is known to you. So you can reduce the size of the problem considerably.
But for real wind generator, if the wind is too high, you have to stop your generator completely.
Yeah.
It produces zero.
Yeah. So there is so that will not happen because we have some constraints in this set. So they will take care of the situation. So if the wind is very high, yeah, then you must stop your generator. So yeah,
You
so
do not account for this.
yeah.
No high winds near location.
Yeah,
Okay.
yeah, that's a good question. Yeah.
But in real life, the problem is that if the wind is really very high, you need to stop your windmill also. So
Yeah.
you need to turn on your power generator also, because wind condition will not suit the windmill. It's a typical problem for many regions.
Okay, so that is something which we did not think of, but yeah, it is something which can be done. But actually, it is not very difficult to put that.
You can make upper cap.
Yeah.
Or limited, it will be two problems.
Yep. Okay, so now you have a new decision variable just like you have z of omega. So there is another decision variable qt of omega, which tells you, so z of omega tells you that entire day in this scenario you satisfied. Q of t tells you, like your question, that did you fail the promise at even one time period during the day or not. More specifically, Q of t tells you that if it is 1 in this scenario, then at all scenarios where wind is more than it, it is also 1. So that means if you satisfy it at some threshold of wind, then you also satisfy it at thresholds above of the wind. So using this, you can make a formulation. So there is a lot of math in it, but what it means is that y of t will be equal to x of t plus some number which is given by the smallest ranked scenario of the wind. So that means your promise will be equal to the generator plus the minimum amount of wind which is absolutely required. For everything above that, these constraints will just be 1. The other constraints serve to say that if you satisfied the promise at 9 a.m. and also at 10 a.m. and also for throughout the day, then you satisfied the promise throughout the day. Conversely, if you satisfy the promise for the day, then you must satisfy it for all time periods in the day also. And there must be some number of scenarios like this. So these constraints are good for us because they represent a totally unimodular matrix. So for this, the linear programming relaxation will give you the exact solution. The problem comes from this knapsack constraint, which makes the problem harder. But this is a much improved formulation from the method with the M in it, and it will give you can run scenarios of the order of, we have tried till like about 10,000 yet, and it can gives you solutions very fast. So the work is not complete yet. What we are doing right now is to study the computation requirements for high number of scenarios using some data from Texas. Then the second thing we want to study is whether this problem really makes any sense. Meaning that you are running a generator with a wind farm. Is the solution that just keep on running the generator whenever the wind is low and keep on running the wind whenever the wind is high? So that means there is no correlation between the generator and the wind. If the answer is yes, then the study does not make a lot of sense and we would need to do some reformulation of the model. If the answer is no, that means that there is a good dependence between the wind and the generator. Then this gives us a good method to have plants like this. So yeah, so this is the end of the first topic. Another thing which I did not show you in this presentation, but we are looking at now, is like a question which was asked. So we are looking at making this x of t stochastic. So constraints of this form, they are in which the randomness is not in the decision variable. They are the joint chance constraints can still be solved exactly. But there are no methods to solve the problem exactly when the decision variable is also stochastic and you have a joint chance constraint. In that case, you have to go to like a L-shaped method or some decomposition scheme using benders to solve this, but it's not guaranteed to give you the exact result. So we are looking at some things in that area also. Okay, so any questions, or we will go to the next topic.
So you said that the advanced model, when your x is stochastic, is more hard to solve, but I think that from the very common sense point of view, the problem becomes simpler, because you can use your generator as a balancing generator, and with many scenarios and with many promises, you can be sure for 100% that you will meet the demand, meet your promise, because you can look at the wind and then turn off your generator and to keep the output as desired.
Yeah.
For a very wide range of conditions.
Yes, that is exactly what we are getting from our preliminary results, that even if you have a threshold of 95, you are satisfying it for 100% of the time. So basically, just like you said, that when the wind will be too high because generator is stochastic, so you will not run it. And
so at least maybe the exact solution of this problem may be not straightforward, but anyway you have a very simple and very good approximate solution which can be drawn simply. Balance your promise and do not promise too much.
So the second, your second statement is not correct, because you have to make your promise ahead of time. So the y is not stochastic. So the total output is fixed, and depending on which is more expensive, the price, the revenue which you are getting, so R or C, which is more, the solution cannot be written beforehand. The other point for this is that if there are a lot of scenarios of the wind which are very small, so close to zero, so then you will not get something like 100% here, because if your generator is very expensive to run, then there will still be some threshold. But it is still...
Can I ask you a simple question? You said that you can forecast or predict the wind behavior. How do you do that? It should be impossible, right?
So we can forecast the wind with the good probability. People do, like, this is a whole area in power system research. So sometimes people build like an auto regression moving average sort of model. You can predict the wind using historic data for the next 2 or 3 hours. You take some data from meteorology and the weather and
Because in this area should be known how wind behaves, right? So they can predict because of, as you said.
yeah, you cannot predict it exactly. There is some confidence bound which you have.
Yeah, I understand. Thanks.
In fact, they're very wide, and you base
Yeah, so
your optimization, your fine optimization on very loose grounds of very imprecise forecast.
no. So this is not what we are using in the optimization. We have maybe like 10,000 samples which are in this range.
So the number of scenarios you consider is about 10,000.
So we are trying
You
it for.
generate 10,000 scenarios. Yeah.
Yeah, but all this is done before the optimization. So we are trying it for different levels. So we tried with like just 250 scenarios, then to make it bigger and bigger until how large can you go. Our reasoning is that the second model, so it should be able to solve much larger scenarios.
Actually, we need only the low profile for wind. Yeah, for each hour we build enumeration of profiles for the less wind.
So you need all the winds, but the model will.
We'll use the low profile.
Yeah, but you don't know beforehand what the threshold is. So it will determine it during the process.
I can reformulate the question. If you neglect the startup and the shutdown costs of the generator, and if you have very fast generator, which can change its power very fast from one period to another, you do not need your scenarios, because you can work with each period of time separately. What you need is just a distribution, the probability distribution of the wind power for each hour of the day, isn't it?
Yeah, so if you can, if you have a very fast generator.
So the generator, the inertia of generator is the only thing in the model which connects together different time periods.
Yeah.
We neglect three lines, bottom lines. You can say, okay, I have this time period, and this time period. I have a probability distribution of the wind in the morning, in the afternoon, and at night. And the problem becomes much simpler.
So if you neglect all of these constraints, so these constraints are known as unit commitment. If you neglect all of these and you basically, meaning you have a very fast generator, you are left only with this. So the problem mathematically is still NP hard, not convex, and difficult to check feasibility.
But you can decrease dimension.
Yeah.
You do not need to consider 100,000 scenarios.
Oh no,
You don't need scenarios at all.
So for this,
what you need is just a probability distribution of wind power for each separate time period today.
So, but
Time periods are not connected in this model.
time periods, but there is correlation in the wind from first time period to the second time period. If there was no correlation, then you can just solve this problem as the product of the probability.
But this correlation gives you nothing, because you can decide at every time period you make a separate decision about how to use a generator.
Yeah, so but our idea is that you want to promise, so the reasoning is that when you make a contract with the system operator, you want to say that I will be reliable. So not like in the morning I am reliable, but in the evening maybe I will not be reliable.
The question is just about the model, not about legal questions. So,
Yeah, hold on.
It's
So,
it's discussion, okay, it's not a question. Okay, thank you.
we can talk after, I guess. Okay, so the next topic is about a hydroelectric energy system. So separate from the first topic, here we are generating energy from water. So the idea is that when you can throw down water from a hill, potential energy will get converted to kinetic energy. You can use this to make electricity. But in a pumped hydroelectric system, what happens is that you can use the electricity to send the water up the hill. So basically what you will do is that when the price of the electricity will be very low, then you will use the energy to supply the water up the hill, and when the price of the electricity will be high, you will generate electricity and sell it and make a profit. So through this system you can always make a profit, that depending on when the energy prices are low or high. Okay, so more in detail, what is happening is as follows. You will make some bid to the system operator. You will tell him, again like in the previous model, that at 9 a.m. I will supply you maybe 10 megawatts of energy. But it is more, the difference from the first model in the bid is that you can also tell him that at 9 a.m. I will take 10 megawatts of energy from you. And you will supply or use this energy to pump or generate to pump water or to generate electricity. The issue is that the price of electricity is stochastic. So if it was deterministic, everything can be done dynamically, but you do not know exactly when the energy prices will be what. Okay, so you can formulate this as a two-step process. So in the so is there a question?
We just probably discussed that we also have such energy system 60 kilometers to the north from Moscow. Exactly like this one. It's
okay.
In valley, it's impressive construction.
Okay, maybe they have some projects for
because
you.
it's 100 meters high from the depths basin to upper basin.
Okay. Okay. Okay.
So the question, you can extract only profit from money, not from energy, right? This project.
Yeah, you cannot store the energy.
You can pump water to the high level and then in the daytime to underneath, right? And can get profit in the difference between prices.
Yes.
That's all.
Yes. But it will become more detailed. There are more considerations which you have to make.
So you can store energy in this way because you can pump more water up to the capacity of the high basin, and it's energy because during high peaks you just run it like
exactly. We will do that.
It's exactly the same system for France.
Yeah, so we
used to balance nuclear power plants with this system of hydro accumulation.
Yeah, we will do this in this model.
In this way.
Yeah, we would do that here also. So we will start with a simpler problem and then we will extend it in these slides.
So, stupid question. Why assume stochasticity of prices?
So prices are governed by what different operators are bidding to you. So what happens is that in the afternoon, people, like in hot weather, people are using the air conditioner more, so the prices go up. And in the evening, the prices of electricity go down. So it keeps on changing all the time.
So it depends on consumption?
On the consumption, on what the supply is, and so on.
Because it's maybe on the market, because you have a market, right? And then everywhere you can give different prices for...
Yeah, it is not government regulated.
Yeah.
So.
Okay, I see.
Okay, so let us start with a simple model. So assume that there is no bidding. So you do not have to do any sort of a bidding. What would you do in that situation? You will see that how much water do you have in your tank. You will see that what is the price of the electricity. you will decide that based on how much water you have and how much is the price, should you throw down the water or should you store the water? And from this first two steps, it will be that either you generated some profit or you had to pay some money. And your aim will be that what is the policy which will generate the maximum profit in this situation. So this can be formulated as a stochastic dynamic program. Your state space is the water level, how much liters of water you have with you, and what is the price of the electricity. At each time you will take an action, should you release the water or should you store the water, and how much. You will have some reward, which will be that either you are making money or you are or you are losing some money through some cost. And your aim in this finite time period stochastic dynamic program is that what is the policy which maximizes your profit. So this is a highly simplified situation, but we will build up on this. So we can write all of this thing down mathematically. So the profit at some time period is the maximum of all the actions of releasing water or storing water of the expectation of the money which you will be making. Meaning that how much money will you make right now at this time period plus in all the future time periods in the day. So the value function for the profit at time t, depending on what is the price of the electricity, P of t, and what is the inventory, that means how much liters of water which you have. So this is the left hand side, is the maximum of all the actions which you can take. The actions depend on how much water you have. So if you have very little water or if you have too much water, you are constrained. So there is some limit that you cannot let the reservoir water go down than maybe 10 liters or something, and similarly for a maximum. So there are bounds on this. The expectation is taken with respect to the stochastic price. The current reward, which is how much money are you making right now, is the price of the electricity converted into how much water are you supplying or are you selling. So this term can be positive or negative depending on either you are making money or you are giving money. And all the future rewards. So this is a recursion. So there is t here and there is t plus 1 here. So you can solve this thing recursively. This is not very difficult to do, and you can solve it for large number of scenarios as well.
And so you assume 100% efficiency of pumping water?
Good question, yeah. So if you do not assume that, then your profits are much higher, because always when there is a loss of efficiency in water going down the hill.
And no evaporation?
No operation cost?
No evaporation of water?
Oh, yeah, no. But we are thinking of putting that into the model also. But so far we haven't added a lot of physics of things here. So far we are just formulating it mathematically. So through this, to understand this recursion, there are some results which you can see. So basically you need some probability distribution of the price. So you need to know how does the path of the price vary throughout the day. Assume that the price varies like geometrically. So for example, if this psi is a log normal distribution, then this is a geometric Brownian motion. So assume that the price varies as follows. Then what will be the result of this dynamic program is that it will give you a threshold policy, meaning that if your price is very high, then you should supply energy, and if your price is very low, then you should buy energy. Of course, depending on if your inventory is very little or very much. So if you have a lot of water and if the price is very high, then you are guaranteed that you will be releasing energy. But it gives you a bound that above a certain value, you should be doing this. So it is very intuitive. It is because in expectation, this price will be is geometrically dependent. Now you can take another dependence of the price, like a mean recursion. So this the meaning of this equation is that in average the price is constant. It is depending. It does not vary too much from its mean. So intuitively you think that there is no incentive to make money because the price is not going to go up, and this is what happens from the recursion. So you either keep on releasing water as much as you can, or you say that I don't want to do anything, because there is just no incentive, no profit to pump. Okay, but this model is very simplified. How is it simplified? There are some drawbacks in it. So in reality, you have to bid to the system operator and say that I want to supply this much energy, or I want to buy this much energy from you. In the previous model, we just said that whatever we will tell the system operator, he will let us do it. So basically, whatever action I want to take, whatever action my dynamic program will tell me, I am allowed to do that and I will get some profit. But you do not know if the action which you want to take will be agreeable to the system operator or not. So you can use the result of the STP only if your bid is accepted by the system operator. So what we will do is that so in the second step, we will create a model which will sort of track the results of the previous model. So it will say that we want to use the results of the stochastic dynamic program. We want to do the same sort of actions which we were doing before. So how should I bid so that the system operator will let me do what I really want to do? So we will submit some bid, which is some amount of energy which we will supply or we will buy at some price. We will win the bid in some situations, which are as follows. So if the STP will tell you that you want to generate electricity, so that means you want to put the water down from the hill. So I want to...
You can have just one bid per period. You cannot suggest alternatives, a menu of bids at each time period. So the price is high and the production is high, and, or another alternative bid if the price will be low. We will do that. Yeah, exactly. But not now.
Right now.
What I see.
So it will be renewable
bid. The only one bid per time period. XT and P.
So hold on, let me go through this slide and I think it will make sense. So if you want to generate electricity, that means you want to throw the water down from the hill. So this is coming from the STP. Then if you really want to win the price, you should say that I will generate electricity at a very low price. So then the system operator will say, okay, you can do it, and you will win the bid and you will get to do what you really want. But first you do not know exactly how low, and you do not know the stochastic city of the price. So you will win the bid but with some probability. So you want to win the bid with a high probability and lose it when you don't get to make your decision with some low probability. So if this did not make sense, so you can look at the opposite situation. So now you want to buy energy. So to let the system operator supply you energy, you will say that I want to give you a higher price than what you are getting in the market. So this is the market price and this is what I am paying you. So if you pay him more than this, with some probability, whatever this constraint will be satisfied, he will supply you energy. So we want to say that with some probability you lose your bid, which is small, but in most of the other cases you will get to do what you really want to do. So there is a previous work which does this in a deterministic setting and which does not take into consideration that you can also buy energy. So we will use something in that spirit. So this figure explains your question. So whatever I just said can be represented as follows. Imagine that you want to buy energy. This is what you want to do. So you will supply energy at you will say that I will give you a high price. 1 minus epsilon is like 0.95 or something. So this is some high large number. So you will say that at the inverse quantile of the price, I will supply you that much energy. This is a high price. So let me buy energy for you. But it is possible that you will lose it still. So with some probability, maybe 5%, you lose your bid, and then you will have to buy energy, but that will happen at a lower price. So it is good for you. It is also possible that you want to buy energy, but the operator tells you that no, you will have to sell energy to me at this time period. Then you will say that I did not want to do it, so you will have to give me a very high price if I will sell energy. So that number is the maximum which you can do for the price, assuming this is finite. Okay, let us look at this one more time. Now you want to sell energy. So the opposite of the first situation will happen. Now you supply energy, you want to sell energy, so you will supply energy at a low price. And you will win your bid with the same 95% probability. It is possible that you lose your bid. Then if you lose your bid and you are selling energy, then you want to sell energy at a higher price because you already lost. So then you will sell energy at some large number. Again, it is possible that you wanted to sell energy, but the system operator says that no, I want to buy energy from you. Then you will say that okay, if you want to buy energy from me, then you will have to pay me a very high price. Okay, so this represents so what did we do so far? The bigger picture is that we had this stochastic dynamic program which tells us that this is what we want to do, but it did not have into account any bidding, so we were not sure whether we will actually get to do what we really want to do. So then we built this deterministic tracking model which says that with high probability you can do what you wanted to do if you bid in the following way. But there are problems with this formulation also. So we assumed that you know how much inventory, how many liters of water you have in your tank right now. But in reality, the way you submit a bid is that at 6 a.m. in the morning, I will say that at 9 a.m., 3 hours from now, I will supply you this much energy at this price. So there is some gap in between the time when you bid and the time when you actually deliver. So you do not know how much inventory, how many liters of water will you have in the future because you do not know what happened at 7 a.m. and at 8 a.m. So in other words, the inventory, the amount of water is also stochastic. And if that is stochastic, that means that the action which you will take, how much water you release or how much water you pump up, is also stochastic, and it depends on what the price of the electricity will be. So for a few minutes, let us step aside from the project and let us look at some general probability results which we will use. So we want to look at given a probability distribution F. So what is the center of this probability distribution? So if you have a model which is like this, so you want to find out the minimum value of x which satisfies the minimum value of x which gives you the expectation of this absolute difference, then the answer is the median of this because it is a continuous. Similarly, if you want to find out the minimum value of x which for this objective, again you can take it to be continuous for simplicity. Lambda is between 0 and 1, so then the answer is the inverse of the lambda quantile. Now you can make x to not be a scalar but a vector. So x is x1 to xn, and then you solve the same thing just like before. Then the answer will be the lambda I. So f inverse of lambda I will be the sum of the x's, and so this result can be obtained analytically, just like these. So why did we do this? We will see in a minute. So there is also one more assumption which we made in our bidding. So far we said that at 6 a.m. I will supply, at 6 a.m. I tell you that at 9 a.m. I will supply you 10 megawatts of energy, maybe at $3. But it does not happen like this in reality. You say that at 6 a.m. you say that at 9 a.m. I will supply you 1 megawatt at 10 cents, the next megawatts at 20 cents, the next megawatt at 30 cents, and increasing like this. So you submit a block of bids. So maybe 10 bids which are increasing. So depending on how much energy I'm supplying you, the price is increasing. So say that you submit a bid with n blocks, maybe n is 10, so here n is not very large. Then you supply some energy at some price, or you buy some energy at some price. Then so the aim is that you want to track whatever we did in the first step of this project, that the SDP gave you some results, no bidding, no very simplified, you just get to do what you want to do. How can we track that model using our current model now? So you want to bid in blocks in such a way that with high probability you get to do the actions of the SDP. So this gives you a formulation for it. It has a lot of math in it, but the solution is very simple. So so just like the result of this expression, you will know exactly how much you want to bid. So
what is your model of the market? What is the dependency of what's the probability of accepting a bid depending on the price you ask?
Sorry?
You need a model of the market, yes, to solve to have a closed form model. So the model of markets in this context means the dependency of the probability of accepting your bid on the bid parameters. You have this.
So you only need the way the price of the electricity is being. You only need the path of the stochasticity of the price. So for example, like this or like this. Epsilon is a parameter, so it is data. It will be given to you. So you say that with...
So inside the forecast of the price. So the forecast of the price is what you need.
Yeah,
to know about
yeah, you only need the forecast of the price. So the expectation is with respect to the forecast of the price, or more precisely it is with respect to the action which you will take at some time t. That is that how much water will you release or pump. The important thing is that is stochastic now. So the amount of water which you will pump or which you will store is stochastic, because it depends on what the price will be in the future. So it is not really an expectation of the stochasticity at that time, but it is a conditional expectation for what you think will be the price at 9 a.m. given that you know the price at 6 a.m. So it seems like a complicated model, but the answer is very simple, because you don't actually have to solve this model. You can just use the analytic expressions from the concepts of probability which you talked about. So you get to know that how much cumulative energy should you bid at each time period, and how much price should you pay as some inverse quantiles. Okay, so we are still working on more results of this model. We want to take some data from some hydro utility. In the US, this is very small fraction of generating electricity. So we don't have good data right now. We only know of Brazil as a very large user of such models. In the US, it is only about like 4% of the entire energy is generated through this. So once we have some data, we should be able to do this. Then we want to solve the tracking model, which is this, for some data. But we want to see how does our actual model, which is this, compares with our STP model, which was the first result. So you know that the STP did not have any bidding. You are just doing whatever you want to do. So that is very optimistic. So it will give you some upper bound on a maximization problem because there are lesser constraints. But we want to study that how far is the gap between this upper bound and the actual problem. Okay, so this is the end of the second topic. I want to tell a little bit more about what I work, unless there are any questions as of now.
Do you have any practical experience in implementation of these models?
Yes, so we have coded these things, and you mean like results, or?
I mean, did you try to simulate some simulation or practical implementation?
So we have done a simulation only up to this step. For the other process, we need some data on from a utility, from a hydro company. We don't have that yet. But it is not difficult to put this thing into code because you know the answers beforehand.
How do you think this model can be applied to a regular station, hydropower station, without any reverse? They have the same problem. They can store the water for the future use, or they can use the current water and to lower the level of their basin.
So how do they store water? They don't have to
They
pay?
don't drop it. They just store.
Oh, okay.
They have a very
They have a natural rate of water.
Oh,
they have
okay, so like a waterfall.
Yeah, water flow.
Yeah. So in that case, the model is more simplified than this. So what will happen is that I think you will not have half of this term. So you will only have like half.
They also have some ecological constraints.
Yeah.
Using the water.
Okay.
So the problems of this sort are called the hydrograph control problem.
Okay.
Hydrograph is the dynamics of the
Water flow. They
water
have
flow
to be-
through the station, through the hydropower station. And you said that you don't have enough statistics for this setting, but for hydrograph control problem you have plenty of statistics in any country. In Russia, for example.
Okay.
Yeah, and then
From the very beginning of the 20th century, you have the dynamics and we have this data also.
Okay, yeah, that is interesting. So two parts to your question. So about the ecology, I do not know much about it. All I know is that they say that the environment is damaged.
A similar problem can be said for the regular hydropower station, and there is plenty of statistics on them
Yeah,
to learn your model and to learn your methods.
yeah, but then the maths is not so interesting. So we also want to do that. We will see how things develop.
Okay, and about statistics, probably, did you consider France? Or the market system of France is not suitable for you? Because in France there are quite big number of such stations.
No, we did not. So maybe I can talk to you after this.
No,
answer.
I'm not specialist in France. Just here is the situation, and they use it intensively for regulating nuclear power stations. You see,
I see.
same idea, because they need to work at the same level. And there are a lot of nuclear stations, quite a big part.
Okay, okay.
From not from me, but from specialists. I think you should look at it.
Okay, thanks.
And Brazil, yeah, have a lot of such.
Brazil has a lot of rivers, so there is a lot, more than half of the energy is from hydro in Brazil.
But it's hydro, not it's pump.
Yeah, they don't need pumped, I think, because of the mountains and the rivers. And so hydro is very little in the US, and pumped hydro, there are only like 10 plants in the entire US for this.
But look at France, because they built it initially for this problem.
Okay, I see. Okay, thanks.
In our country, only one such.
Okay.
70 kilometers, 60, 70 kilometers from Moscow.
Well, it's good for you. You can get some data and work on it then. Okay, so I will be graduating next year. Right now I'm in my 5th year of my PhD. Other than research, I have worked in industry. This is a pharmaceutical company. I worked there for a summer as an internship on optimizing the distribution system. So how should you send out couriers depending on the weight of the pharmaceutical which you are sending? So what is the logistics of things? This is a semiconductor company, so they have an assembly line on which things are produced. So you want to optimize the flow of parts on a machine line. Then I worked at some IT solutions company in Prognoz in Russia. So they had this in Piram. So they had this project with the Sberbank that they want to send out money in trucks. So what is the shortest path which a truck should take? So basically a traveling salesman problem. In terms of research interest, so my interest and a little bit expertise is in stochastic optimizations with applications to healthcare. So this talk was not about healthcare, but I am giving another talk in St. Petersburg on healthcare and on renewable energy, which are these two topics. So specifically on healthcare, I work in public health. So in pandemics or in epidemics, how should you distribute vaccines and antivirals to people? In terms of teaching, I have interest in the following courses to teach. So linear programming or modeling of operations research, and basically courses in optimization, but not so much in nonlinear optimization. Okay, thank you.
Yes. Actually, there were so many questions during the talk, so that's okay. I guess the talk was of interest for us. So thank you. Ладно, все, вот это на этом заканчиваем.